So let's begin with welcome Joe Kileel from Princeton. So he'll speak on orbit retrieval with applications to cryo-electron microscopy.
Okay, thank you for having me. So the various projects I'll talk about today are all team efforts. I thank many collaborators, particularly my current postdoc advisor, Amit Singer at Princeton, and also Afonso Bandera at NYU. So I'd like to start with the motivating application for which we'll build a model called cryo-electron microscopy, cryo-EM. This is an inverse problem. You want to get a 3D protein structure from 2D images. This illustration is a toy example. So you have Mickey Mouse, that's a 3D structure. And what you get to see are many 2D images indicated by the heat maps. So in cryo-EM, an image is captured by an electron microscope. You can think of it as shining a beam of electrons. The electrons pass through the 3D structure and interfere. And then effectively what you see in the image is a line integral of the 3D structure. So the 3D structure is some electric field, and you're seeing line integrals of it.
So like, do you mean that the color represents the length of the fiber over?
The color is the value of the line integral.
Okay. The line integral is just length of the intersection, or not?
No. So this 3D structure actually you should think of as a function from R3 to R. It's the electric field generated by the molecule. This is what cryo-EM detects with the electrons, the electric field. And so you have this unknown function from R3 to R, and some orientation, it's rotated, and then you take line integrals, some in the z direction of the rotated function. And that's one observation.
So by the way, for Mickey Mouse, why do you need the microscope?
This is just a super simple example, right? to illustrate what we're talking about. So you can, the orientations of the individual images are unknown here. Okay, so in practice, the molecule is frozen in a super thin layer of ice, several copies of the molecule, and at time of freezing, you have no control over the rotation each particle picks. So there are unknown rotations for every image here. But anyways, you get the images. So in this example, it's kind of easy to see actually that it's Mickey Mouse. So even from this, maybe like this single image gives you a pretty good indication of what you're looking at, I think. Okay, just visually, I claim.
Just to clarify, so you mentioned that we're actually searching for function from R3 to R, so the actual Mickey Mouse is like a level of value of functions.
What I'm plotting here is a sub-level set, yeah.
It's a level, okay.
Yeah. And then the color in the images, so the images are functions from R2 to R, and the color is indicating the value.
Okay.
So that's what this means.
So in practice, is it always you get many identical copies of the molecule pretty clearly separated, or are they often on top of each other's?
They are quite clearly separated because the layer of ice is made to be super thin, so that there should really only be like one particle. There shouldn't be two particles on top of each other. Okay, but yeah, let's see what actually the real data looks like. Okay, this is a real cryo-EM image, this one here. It's called a micrograph. So every faint little circle in that image is a single particle. Okay, in one slab of ice, one micrograph. And so you can see they are kind of clearly separated, but there's tremendous noise there. It's nothing like the very clean Mickey Mouse images that I showed. So in practice, you're getting many of these micrographs. Each one has maybe 300 particles on it. Altogether, you maybe have 100,000 particles. Each one has an unknown rotation matrix. And your task is to go from the super noisy images to a high resolution 3D structure. So visually, I think that this is a hard problem because of the noise and the unknown rotations. Any questions about this? So, in the life science community, cryo-EM is getting attention. About a year ago, it received the Nobel Prize in Chemistry, awarded to 3 pioneers. Right, so the citation says they got it for developing cryo-electron microscopy for the high-resolution structure determination of biomolecules in solution. Okay, so some of the promise of cryo-EM is that sample preparation is quite easy. You just have to freeze particles in ice. You don't have to crystallize. Sample preparation is easy, and also you get to see the particles in solution, more or less, because you're freezing them in solution, and so they don't change much in that instant of freezing. So you see them more in their natural state than if you were to crystallize. So that's why it's exciting. And already in 2015, cryo-EM was recognized as Nature Method of the Year. Okay, so I actually want to talk about a class of recovery problems today with group actions. And so an easier example to think about mathematically is this 1D problem, multi-reference alignment. So look at the left column. There is a gray ground truth signal that you see, and then it's being cyclically shifted in that left column. You have the same gray signal, but it's being cyclically shifted. You can think of it as a function from the circle to the real line. And now what you get to see are the red dots. So the constellation of red dots is one observation. So it's a sampling of the shifted gray signal with a lot of pointwise noise. So you see many such observations, and your task is to try to recover the ground truth gray signal. So this is in the spirit of cryo-EM. The gray signal is like the molecule. It's being rotated around the circle with a lot of noise. Okay. So that's MRA. So here's the common framework. This is the class of problems I want to talk about. So let G be a compact group acting linearly on a real vector space, RL. So you can think of G as SO3, and it's acting on some finite dimensional space of functions from R3 to R that's in which the molecule lives. Let pi be a fixed linear projection from V to W. Okay. This plays the role of tomographic projection in the imaging. And now let X be a fixed vector in V. So it's like a fixed ground truth. Right, so you've got G acting on V, a projection from V to W, a ground truth in V. Now suppose we observe IID realizations of this random variable Y. It's G acting on X, which is fixed, projected by pi, plus epsilon, which is noise. Here G is a random group element. So at this point in the modeling process, let's take G to be uniform over the compact group. We're going to come back to that. It's very important. And let's let epsilon just be Gaussian noise. Okay, white noise with variance sigma squared. So we should think of sigma squared as very large if we want to capture cryo-EM. So now the task is to try to get back x from many observations. Now, of course, you can't hope to get x itself back because of a global ambiguity in this problem. The best you could hope for is to get the group orbit that x lies in back. So we're trying to estimate the orbit of x. Okay.
So when you say you're trying to estimate the orbit, which form of the output would you accept? Like any representative of the
Yeah,
orbit?
I would accept any point in the orbit.
Okay.
Right, so there's, like, of course, there's the Euclidean norm on V, and then that induces a metric on orbits because it's a compact group here. So I want to get a representative signal such that its orbit is close in that induced metric to the ground truth orbit. Right, so this captures the two problems we talked about. MRA, the 1D signal. There, the discretized signal lies in R to the L, where you have L samples, and you have the cyclic group Z mod L acting by cyclic permutation. There's no projection. For cryo-EM, the group is SO3. The vector space where the molecule lives, those are band-limited density functions. So you can think of the molecule as you can imagine expanding the molecule in spherical harmonics multiplied by some nice radial functions, and then truncating that expansion at some degree of spherical harmonics to get a finite vector space of functions.
When you say that this is SO3, how do you know what's the center?
So that's a very good question. We're going to assume that all the images are centered. We're going to assume that we can center the images, by which we mean that in the middle of each image, we're seeing a projection of some fixed point in the molecule.
And is that realistic?
Centering can be done somewhat well, but you still can be off by a couple of pixels or something. So this, yeah, like maybe enlarging the group to include translations would be nice, but then you lose compactness and we don't quite know how to do it.
And you say again about the cyclic shifts, how did they appear in that example?
So there's a ground truth gray signal, okay, and it's being cyclically shifted.
Related to R to the L.
So R to the L, we say that the ground truth signal, we imagine it discretized at L points.
Ah, okay.
Okay, equidistance points, and then we're cyclically shifting. So I've drawn the gray as a continuous signal, but really it's L points.
Okay, thank you.
Okay. Okay. And then you do have a projection for cryo-EM. And the key thing is that it's just linear. It's a linear map from 3D functions to 2D functions.
And what are the typical values of L you would like to work with?
So for cryo-EM, it's a few thousand. So it's pretty high dimensional. So let's think about maybe the most natural way we could solve this problem. What we might try to do is estimate each unknown group element per observation. And so we might try to estimate each rotation for cryo-EM or each shift for MRA, observation by observation. However, for high enough noise, this is actually fundamentally impossible. So accurately estimating rotations is impossible, even if you know the ground truth molecule, if sigma squared is too large. So I'm just going to leave it as a as a rough statement that you can't estimate rotations. I won't give you a precise theorem, but it is in the literature. Okay. So how to get around this? What the state of the art does rely on the leading software for cryo-EM. It takes a Bayesian approach. So Reliant does not try to estimate one rotation per image. It rather makes soft assignments for every image. So it holds a probability distribution over SO3 for every image, indicating its confidence that that rotation is the actual rotation for that image. So 100,000 images, it has 100,000 soft assignments, 100,000 distributions over SO3. And what Reliant does is it iteratively estimates soft assignments on rotations, and then holds those fixed and estimates the 3D structure for the molecule. Holds the molecule fixed and updates the rotation guesses back and forth. This is called iterative refinement. It sort of works in practice, but it has drawbacks. One is model bias. You have to input an initialization to the 3D structure to get this going. Another is that it's extremely computationally intensive because you're updating all of these soft assignments for 100,000 images. And finally, this lacks rigorous guarantees. So what we try to do is a different approach, which goes back to a paper of Zvi Kem in 1980. It's also called the invariant features approach. So to bypass the estimation of the individual group elements, one could try to average out all of the unknown group elements by computing moments of the data set, of the observations. So you can try to average out the uncertainty. So what does this mean? So remember, our samples are IID draws of Y. The first average we could take is just the sample average. So for enough samples, that should be close to the population average, averaging over G and epsilon. Okay. So epsilon averages to 0. Pi, since it's linear, you can pull out of the expectation over G, and so you get that expression. Okay. Pi of expectation over G of G acting on X. So it's an average over the orbit. This is what the first moment tells you. Okay, the sample second moment is close to for enough samples, it's close to the population second moment, so it's almost the covariance.
So what does that tensor square means? Mean that just you take vector y and Kronecker product of itself?
Yes.
Or, so it's like one rank matrix.
Yes.
Okay.
Great. So y here would be like the value of the image over at every pixel. So it's a very big vector. And then y tensor squared is you take any 2 pixels and multiply the intensities there.
Okay.
And then you average this over the entire stack of images. Okay, so for enough images with respect to the noise sigma squared, the sample average is close to the population 1, and that admits this expression on the right. So there's this red term. You average over the group of G acting on X, Kronecker product with itself, plus some bias term, which you can remove. So bias term you can remove once you know the first moment. So you more or less just get that red term.
What is sigma in that text in the last line?
So sigma squared is the variance on the noise. Right? The noise.
Ah, it was from the okay.
Yeah. Right.
Okay.
The Gaussian noise. So you should think of sigma squared as very large. So for these estimates to be accurate, you need for the dth moment estimate to be accurate, you need on the order of sigma to the 2D samples. Okay, that brings the variance of the sample moments to order 1.
And what is the meaning of this approximately equal?
So like the left-hand side will have, in expectation, will equal the right-hand side, and it'll have small variance for enough. So the left-hand side is random, right? Depends on the samples. It's the sample average. In expectation, it equals the right-hand side, and it has small variance for enough samples. So with high probability, it's close. Okay. So these red terms, does anyone recognize what these are?
Are moments,
Right. But
and then in terms of group, or
yeah, in terms of just invariant theory. So you have a group acting on a vector space, you take a vector in it, and you average over the orbit of tensor powers of it. So this is the Reynolds operator.
I mean, so this is just to take like polynomial ring and apply averaging over a compact group.
Yeah.
Okay.
So here it's like, yeah, exactly. We're taking the cubics in X and then we're averaging over the compact group. Do you have any question?
Yeah. So
I'm still trying to understand that. I don't know how to read this.
maybe so the left thing will converge to the right thing if you will do many tries, for example.
Conversion in what sense?
In the sense of probability distribution, because like the left thing is random. Left sample average is random. You make several experiments and you average results. It's still a random number.
Yeah, but it's a sample second moment.
Yeah.
It's also yes. It's like
Sample moment doesn't mean okay.
It doesn't mean moment. Yes.
Okay.
So, yes.
Sorry,
Yeah, so there are sample moments and population moments. And if you have enough the samples are random, sample moments are random, but they converge to the population moments with enough samples, enough observations. So what you should think is just, you have approximations to the right-hand side, to the red terms, with projected by pi. Okay, you have these with a little bit of noise. Okay, and so your goal is to try to estimate the orbit. So the invariant features approach is to estimate enough moments by sample averages first, so that you have enough population moments for the orbit to be determined, right? And then you want to actually try to get the orbit by solving a noisy polynomial system. Okay. So you know you have the value of the orbit on a bunch of invariants with a little bit of noise. You know that those invariants are enough. Say you've worked out that those invariants are enough to determine the orbit. Now you actually want to get the orbit back. You want to solve this noisy system somehow. So that's a big part of the problem. Okay, so in case by case, we deal with it in a case by case basis. Like generically, what you can do is a sort of least squares, a non-convex least squares, and hope for the best. Okay, but then you're losing guarantees. So. Okay. So the red terms, as I said, those are the low degree invariants. Those are in the invariant ring. Okay, those are exactly the low degree invariants in the invariant ring. And now if you have a projection in the problem, you may not get to see all of those. Okay, you'll just see some subspace of the low degree invariants. But okay. So I want to walk through the process for the 1D problem with shifts. Okay. So there's no projection for that, so it's a bit easier. Okay, so you have the invariant ring of R to the L under Z mod LZ. So what are the low degree invariants, and how do you invert them? Okay, well first off, Z mod L is finite abelian, so we can diagonalize its action over C. And the discrete Fourier transform does that. So when you pass to the Fourier domain, shifts now act by modulating phases of the Fourier coefficients. Right? So you have a shift S, it lives in Z mod LZ, and it acts on X hat, the Fourier transform, the kth coefficient, by multiplying by this unit modulus complex number. Okay, modulating by like S times K. So then what are the invariants of this action, this diagonal action? Well, since the action is diagonal, the invariants are spanned by monomials, right, for a diagonal action. So the linear invariant is just X hat of 0. Right? So you can see if K is 0, then the left-hand side equals the right-hand side for all S. That's it. That's the only linear invariant. What about the quadratic invariants? So what are the quadratic monomials? Well, I claim that they're just X hat of K times X hat of minus K. So why? If S acts, then it modulates X hat to the K by like S times K, and it modulates X hat minus K by minus S times K, and these cancel. So you can see again, left-hand side equals right-hand side for all S. If you apply to that, you apply S to that quadratic monomial, and similarly with the cubics. So those are exactly the invariant cubic monomials. And you can keep going. For a higher degree, it's clear how to proceed. Okay, so suppose we had these red terms exactly. Let's just disregard noise for a second. We had their values exactly.
I'm sorry. Is it true that like these three actually generate the whole ring, right?
They don't generate the ring.
They don't generate the ring, really?
Not the ring, no. Okay, so we're going to come, there's subtle differences in notions of generation that are important here, and they do generate something. They generate the fraction field of the ring.
Ah, yes, fraction field, right, because you have to do, yes. Okay.
Yeah. Mm-hmm. Right, so our question is, do these moments tell us the orbit of X hat? Or do we need more invariants? Well, certainly just the linear and quadratic invariants are not enough. Okay, that's totally clear. There's just not even enough invariants. There's like L over 2 invariants there with L unknowns. But actually, with the cubic invariants, those do determine the orbit of X hat, at least for generic X hat. So
Yeah, but like this is actually because they generate fraction field, right?
Yes.
So you can. Okay.
But we can see it super explicitly. So assuming all of the DFT coefficients are non-zero, here's how you get back x hat if you knew the values of these invariants. Exactly. So you multiply a bunch of the cubic invariants, and then you divide by several quadratic invariants, and this recovers x hat to the 1, x hat of 1 to the nth power. Now just choose an nth root. This essentially kills the group ambiguity once you choose an nth root. Right? The ambiguity of the group is exactly an nth root of unity. So just choose an nth root here for x hat of 1. And once you have x hat of 1, you can easily get back the other DFT coefficients. So this tells you how to get back the orbit of x hat, provided all the DFT coefficients are non-zero. Okay. So what we've shown here is that under that hypothesis on x hat, right, the cubic population moments are enough. Now what about with noise, right? So what if we have noisy values for these invariants, but just a little bit of noise because we averaged over 100,000 images or something. Well then, multiplying and dividing like this doesn't actually work very well. It's not very numerically stable. So it turns out that you can think of better ways to do this inversion, and one is actually by a certain eigendecomposition on the bispectrum. And actually even better is just least squares fitting, just empirically. Okay, so.
But you still use only these three.
Yeah, you just use these and then do least squares, and it actually works as well. But without any kind of proof right now. Okay, so these are the sorts of questions that come up in orbit retrieval. Right? What are the invariants? To what degree do I need to go for the population moments to determine the orbit? And how do I recover? How do I solve for the orbit? And how do I do it stably? This is a theorem that's telling you invariant features is a good thing to do.
Whose theorem is this?
This is, so it's in this paper with Alfonso Bandera, Ben Bloom-Smith, myself, Amelia Perry, John Weed, and Alex Wien. Okay, so
what's x prime?
okay, so let's just go through this slowly. So in fact, invariant features is sample efficient, meaning that among all possible estimation procedures, invariant features gets away with the fewest samples. Okay. So
This is for all.
for all, yeah.
For all x prime.
For all estimation procedures. So let x be the ground truth.
No, I mean for all x prime before like the first line of the statement.
Yes, for all x prime, yeah. Okay, so fix x, and now let d be the least degree, possibly depending on x, such that for all x prime and x having matching moments up to degree d implies that their orbits are equal. Matching population moments implies that the orbits are equal. So then any estimation procedure, whatever, requires on the order of sigma to the 2d samples to accurately estimate the orbit with high probability as the noise goes to infinity. So what I'm telling you here is the dependence on the noise and the number of samples you need. It scales as sigma to the 2d, where d is this cutoff degree for moments to identify orbits.
Does the theorem actually provide not just big O growth, but actual number?
We have some weak estimates on it. There's signal dependence in the big O, but it's not completely understood right now. But you could imagine, like, so I claim that the dependence on the noise is what's most important to understand here, because the noise in cryo-EM is so high.
But the constant is not.
The constant is not known right now.
It's not known, but it's not a huge number. You don't know.
I could get back to you after the talk.
Okay.
I have to check.
So, but like this big O, it is not uniform in X,
No.
right? So for each X, it's like maybe all its own big O.
Yeah, that's right. Yeah, it depends on X.
And what's the dependence on the probability of accurate estimation? Or
So for sigma squared above a certain explicit threshold, the high probability is exponentially close to 1.
okay.
Yeah, the big O also hides a dependence on how accurate you want the estimate to be. So there's an epsilon here. So I'm really short on time right now. Just to say a couple of things about the proof. This is an information theory result. It's not my expertise, but the key quantity to compute is the KL divergence between probability distributions for an observation when the ground truth is x and when it's x prime. So the Kullback-Leibler divergence is some kind of distance between probability distributions for observations here. And one can upper bound this distance by a Taylor expansion in 1 over sigma squared, where the constants are expressed in terms of the difference of moments.
What's HS in the subscript?
Hilbert-Schmidt. Okay, so this is the key computation. So you show that if you have matching moments up to degree d, then the KL divergence between x and x prime is low. It's so low that you actually then can argue you can't hypothesize tests between x and x prime unless you have orders sigma to the 2D samples. And if you can't distinguish between x and x prime, then you certainly can't retrieve x. So that gives a lower bound. That style of argument is called Lecam's two-point method. And then invariant features actually meets this bound. So this is tight in the dependence on sigma. Okay, so what it means practically is invariant features for cryo-EM ought to use the fewest number of images sort of possible. Okay, so that theorem begs the question of what is D? What is the minimal degree D that identifies orbits? So sample complexity for orbit retrieval thus is answered by purely algebraic questions about invariance. Right, so back in the theorem, right, in these equations, these are population moments. So there's no noise in this system of equations. So we're just talking about invariant polynomials determining orbits. So if you want unique recovery, by this we mean that for all x, for all ground truth x, you would like the degree d moments to uniquely identify the orbit of x. Then what you're asking for is that the degree d invariants generate what's called a separating subalgebra of the invariant ring. So you're asking for something like ring generation of the invariant ring. If you would like to be able to uniquely identify the orbit for almost all signals x, for a Zariski open non-empty subset of V, then it turns out you're asking for the smallest degree d such that the invariant field is generated by the low degree invariance. So you're asking for field generation if you just want to be able to retrieve almost all signals. You could ask for something even weaker. You could ask that for almost all signals x, the invariants up to degree d don't determine x, perhaps, but determine a finite list of possible orbits on which x is. So you might ask that for the smallest degree d, such that there are finitely many consistent orbits.
May I ask a question? So when you say that it's unique recovery, it will be it's sort of strongly unique because like it's unique even over complex.
Yeah, that's right.
So, but if you would like to find a unique real number, you might relax the condition on the d, right? In principle.
Okay, that's a subtle question. I have to get back to, I'm not sure if there's a difference between separating subalgebras over the reals and over the complexes. Maybe we can talk about that.
Okay, sure.
Yeah, so indeed all of these things will give you uniqueness over the complexes in these senses. Okay. So by the explicit formula before, the 1D problem MRA has invariant fraction field generated at d equals 3. Right? Because I told you how to get back the orbit, provided that x hat had all non-zero entries. So I showed generic unique recovery. So then the theorem tells you that you need on the order of sigma to the 6 samples to recover the ground truth by any estimation procedure for MRA. Let me remark that this bottom condition, generic list recovery, which maps to the weakest notion of generation that we have here, this can be efficiently tested on computer by the Jacobian criterion. You're just asking when is a map quasi-finite, a polynomial map. Let me also remark that ring generation in invariant theory is quite classical, I think, but this field generation notion there's very little work on it actually, as far as I can tell. So the middle condition. And yet I would argue that from our point of view, the middle condition is what's most relevant. We would like to have an algorithm that works for almost all molecules. We maybe allow some worst cases. Okay, so these are the algebra questions about generation. So let's go back to cryo-EM. So what is D for cryo? So this is our theorem in the same paper with Afonso et al. We found that cryo-EM has generic list recovery at d equals 3. Okay. So you need to go to cubic moments. We also considered a variant of cryo-EM with no projection, no tomographic projection. So there, each observation is just a rotated molecule with a bunch of noise. You have 3D observations, say. 3D images. So then we can actually show that you have generic unique recovery. not list recovery, at d equals 3. And moreover, we gave an efficient way to invert the cubic, quadratic, and linear invariants. Okay, so just to point out that the cryo situation is much harder than the multi-reference alignment problem. Okay, so I'm showing you here what the actual invariants are. So the top bullet, so the second bullet from the top, these are the invariants for cryo with no projection. Okay, the variables here are the x's, and they're triply indexed somehow or another. Then you've got some complicated coefficients in these cubic invariants. These are Clebsch-Gordan coefficients for SO3. Then the invariants for cryo with projection are certain linear combinations of these unprojected invariants. And the linear combinations, again, are quite complicated. So they involve, again, another Clebsch-Gordan coefficient and then certain special values of spherical harmonics.
Is it like something classically known? What's the degree of just generators of the whole invariant ring of SO3?
So I don't know that that's classically known.
It isn't? No, I'm
Not to my knowledge, but even if it were, that's the strongest notion of generation. That's not really what we're interested in.
Yeah, that's right, but maybe it's 4, right? if it's 4, you'll be happy, right? Or not?
Maybe it's 4. I doubt it's 4. I think it's probably much more than...
Just fantasy. Okay,
yeah.
Okay. So, but you just don't know this number.
Yeah, we don't know this number, but like, it's probably much more than 3. It's probably not a constant.
What do you mean by not a constant? But you have like a single group.
A single group, but then it's acting on some representation, right, of SO3. So.
But this 6 is uniform in the.
Yeah, it's uniform over like a certain range of representations.
I see.
Of SO3.
I see. Okay, yeah, now that makes sense. Okay. Yeah.
Okay, so I'm actually almost out of time. So we put these ideas to practice with the Mead-Stingers group. We didn't quite do invariant features all the way. We calculated linear and quadratic invariant features and then used a little bit of extra data to avoid calculating cubic invariants. Our input was a real data set for yeast mitochondrial rhizome. We had 350K images, that's one of them. We ran our invariant features like algorithm. We used here least squares, actually, to try to invert the moments. So did some actually some manifold optimization there. And these are the results. So for the molecule, the blue is its 3D structure. So this was known through another independent imaging technique. So that's the ground truth molecule. We expanded this molecule up to a certain band limit. And so the yellow is the low pass of the ground truth up to the band limit that we were trying to solve for. Okay, so we were trying to get the yellow. The gray is what we obtained. Okay, and you can see that the gray does quite resemble the yellow. So this procedure, it isn't the best. It's not giving you exactly the yellow. It's certainly not giving you the full high resolution molecule at our current stage of development. But it is, I think, giving you a good ab initio model. So if you were to take the gray and then plug it into iterative refinement, I think that that's better than just Yeah, I'm choosing an initialization in some biased way. Okay, so I'll say a couple of words about ongoing work. So one important assumption to relax is the uniformity over SO3. This doesn't hold in practice. So in practice, molecules have preferred orientations. So what one can try to do is treat the rotational distribution as an unknown, and the molecule as an unknown, and try to solve for both the rotational distribution, which is non-uniform and unknown to you, and the molecule. Right, so how do you represent the rotational distribution? It makes sense to expand it in matrix entries of the irreducible representations of SO3. That gives you an L2 basis of functions on SO3. So you expand up to some representation, and then you treat, so you have these B's representing the molecule and X's for the, so B's for the distribution, X's for the molecule, and you try to solve for X and B from moments. Okay. So what we can say is that, wow, yeah, something surprising happens. Okay.
You expect to prove this, or
19, it says 2019.
Yeah, that's 2019. So it's 2019 because we're gonna submit a paper in 2019.
okay, okay.
Yeah. Yes.
But like,
That's not the surprising part. The year is.
Is better than the theory you had?
This theorem is better. Yeah. So this is.
In sigma, right?
Yeah. This is telling you d equals 2. You only have to go to linear and quadratic invariance for certain choices of band limits on the molecule and rotational distribution, if the distribution is non-uniform and unknown. So this is very surprising, I think. An unknown non-uniform distribution is in this sense easier than a known uniform distribution.
How come?
So you just do the computation. You write down what the moments are in terms of x and b, and then you can, so you have a map from x and b's to linear and quadratic moments, and then you can compute the Jacobian of this map and
but
see
just
that it's
like, isn't the uniform case a special case of unknown?
Yes, it is. But when you compute that the Jacobian matrix is full rank at some point, that only tells you that that almost all fibers are finite.
So what you mean is that uniform distribution hits into the bad set of this map.
Yes.
I see. Okay, good, thank you.
Okay, so this, as I wrote, this is a computational algebra statement. But we're actually trying to make it practical and develop a non-convex solver. So just doing least squares to solve for x and b, matching to the first and second moments. Can we actually invert the map in practice? So when you try to build a solver, the question is not just now about finite solutions, it's also about conditioning of this map. So we believe that the map might be too ill-conditioned here to actually be able to invert it. This is work in progress. We have to deal with conditioning issues to try to get this solver. This is another step, and it goes beyond just the algebraic statement. Actually doing this. So my co-author Nir Sharon presented this at a Princeton Nature Conference in the summer. Preliminary results of this. Okay, I don't think I have time for the last extension. I don't know. I just have 2 more slides.
This is good. There is time for 2 more slides.
Okay. So this is another neat extension of orbit retrieval. So often data sets contain images of various molecular conformations. There's not just a single particle that you're seeing rotations of. Maybe there are 10. We thought about a discrete number of conformations previously, but maybe even there's a continuum of conformations. So there's a flexible molecule, say, and it's continuously opening and closing in some portion of it. How could we try to recover a continuum of conformations? So here's a testing ground, another play problem to analyze, and it's MRA, continuously heterogeneous MRA, multi-reference alignment. So suppose you have some signals, on the one-dimensional signals on the circle, you have k of them, S1 to k. And now what you see is a signal in the span of S1 to Sk, something in the span, cyclically shifted with noise. So suppose in the R to the, now the notation is now R to the n. In R to the n, there's some k-dimensional subspace, so maybe 2-dimensional. You're seeing a point on that 2-dimensional subspace cyclically shifted with noise. Your task is to maybe recover the subspace, recover the signals that gave you a basis of that subspace, up the shifts. So this is the very simplest model for a continuum of conformations. It's just when the conformations are low-dimensional linear subspace. But even then, it's very interesting mathematically. So it turns out that this relates to the following funny kind of symmetric tensor decomposition. Great. So symmetric tensors, just to remind you, you can think of them as homogeneous polynomials. So suppose you have a homogeneous polynomial of degree d and n variables, capital F. Let's try to decompose it as a sum in the following funny way. Write capital F as little f1 up to little fr with r minimal, such that each sum end, fi, has a special simple form. So it ought to be a degree d polynomial in k-linear forms. Okay, so we have capital F, it's degree d and n variables. We're trying to write it as a sum of polynomials degree d, which secretly can be written in k variables. This is kind of a strange thing to do. So if you take k equal to 1, right, then each fi you're asking it be a degree d polynomial in one linear form. So that's just a dth power of a linear form. So if you set k to be 1, you retrieve CP decomposition for symmetric tensor decomposition. You're trying to write f as a sum of powers of linear forms. If you take k to be 2, you're trying to write f as a sum of polynomials which can be written in just 2 linear forms each. And those linear forms can vary from term to term. This is a new kind of decomposition, but it's actually what comes out of continuously heterogeneous MRA. So I don't want to, we do have a result in this, but I won't state it here. We're working on ways to do this decomposition for small r. And it turns out that the key idea is called apolarity, which is useful for classical CP symmetric tensor decomposition. And what you should do is you should take your capital F and you should look at linear differential operators that kill F. And those somehow contain a lot of information about F if F happens to admit a low rank decomposition in this way. Okay, so this is also work in progress. So here's the wrap up. I told you about general orbit retrieval. It models estimation problems with group actions, particularly cryo-EM. At low signal to noise ratio, I claimed that rotation estimation is fundamentally impossible, while invariant features is sample efficient. This leads to various algebraic problems about generation by low degree invariance. Actually, inverting moments is polynomial solving or optimization. Things like conditioning come into play. Add-ons to the basic orbit retrieval model. I told you about non-uniformity over the group and heterogeneity. Those are work in progress, as is further implementation with real data. Thank you.
Thank you. Question. So how do you solve a noisy polynomial system?
So in practice, you're just going to do some optimization.
And what do you assume from
So
the
if you happen to have an algorithm that works in the clean case, in the noiseless case, then you could just run it with noisy moments and see how stable it is. That's one thing.
Do you have an algorithm that works in the non-noisy case, and what is the algorithm?
So not for cryo-EM, no. For MRA, I just showed you this way to the multiply and divide invariance. So back here, right? That's an algorithm that works in the noiseless case. You can plug in noisy moments.
For cryo-EM, say, the obstacle to do something like homotopy continuation is just like huge dimension, right? Or
Yeah, that's the main obstacle. It's also vastly overdetermined. So you have way more invariance. You have thousands of variables, but you have even more invariance. So it seems like you would have to square up, and you'd have like bazoo many solutions to the squared system.
I have also a question about the noise. So when you work in your like formal setup, right? So you have the diagonal covariance matrix for noise, right? And this means applied to the molecules. This means that you have the same noise in all harmonics.
Yeah.
Is it like what actually happens?
No, this is a simplification.
So, but like more realistically, would you say that you have pointwise white noise or
Pixel what?
yeah, or what would be a realistic assumption on noise?
Yeah, certainly not this. I don't.
Oh, maybe I'll put it a different way. So, for example, if I replace ik with a fixed diagonal matrix, does the like theorem and all the methods work?
That I don't know. Yeah, I'd have to look more, think about that.
So if you had a single polynomial and one unknown, what would you mean by solving in your sense?
A single polynomial and one unknown. So you should really think of an overdetermined system. So say
Okay,
two polynomials and one unknown.
Okay, so what?
So now we're talking about these polynomials don't have a common zero. But what we could try to do is like minimize the squared residuals. So you just have f and x.
Maybe we can take example with complete FNG.
You could try to. one thing you can try. So you want to think of a concrete example there. Okay, so x plus 1 equals 0.
And x equals 0.
Okay, sure. I mean, okay, fine. I mean, that's an awful lot of noise, though, because those aren't even close to intersecting. Maybe we should think of something like 0 and 1. So then, I mean, we're talking about something like this. Right, so just think of it geometrically, maybe. So x plus y 1. This. And then minus 1. So a near miss like this is what I would mean.
Okay, and so you are not solving polynomial systems, right? So you just call some other thing solving polynomial system.
This here. So yeah, this.
So you just so
In the clean case, right, with in the noiseless case, we can think about solving the system.
it will still be overdetermined.
It will still be overdetermined, but in the clean case, it will admit a solution. We could try to find some way of solving it.
And
Then we could plug in noisy moments into that algorithm.
And what will be the precise meaning of solving?
In the clean case,
Yes.
it would just be finding a point in the orbit.
So in terms of just polynomial systems,
Finding a solution.
find the solution. That I don't understand.
You have a system, an overdetermined system of equations, which does actually admit an exact solution. Find it.
Yeah, but it has real coefficients, and you're looking for a real number, or for what kind of number you're looking for a solution? Or you're looking for a point in the box and an interval. So what exactly do you mean?
I mean, you could work in a. So the coefficients are all algebraic numbers here. You could work in a number
symbolic,
field.
symbolic solution. Find a symbolic solution.
In practice, a floating point approximation to it will be enough, but I mean.
And when you do this, what about certification, and what about guarantees for errors?
Right, so that we don't have, because we don't have a good algorithm right now for cryo-EM.
Which ones? Because it's two parts. Do you certify your anything in?
Okay, let's go to this, right? So this here is like a symbolic algorithm. Okay, so this is what I would mean by solving something like this. So I mean, I don't really need to certify anything here, right? Okay.
Yeah, that's- So elimination. We call this elimination.
Yes. Yeah.
Okay, so but like this argument approach, right? It's very sensitive to scaling of equations, right? So if I multiply some equation by 2, I will get a different root, right?
That's right. Yeah.
So do you somehow specially normalize your invariants, or you just leave them?
We do. So we put a weight on on the second moment, we downscale the second moment so that it's how to say, so let's.
Also, by the way, so may I just finish with that question? So you showed that the formulas, you just the ones. Could you show them?
Yeah, show them. Okay.
How could you possibly get them from over the not the ones with the hats and yeah. So how would you possibly get this from overdetermined system? So how would you symbolically solve an overdetermined system and get not just 1 = 0, but actual other things in a meaningful way?
So it's what I'm doing here, right?
Suppose the system has no.
But it has solution.
I am doing it here.
That's the
So
point. So
I'm
it has
saying-
a solution.
right, you know the value of all these invariants in red. Suppose you know them exactly. Okay, so as algebraic numbers.
So that, the example that you produced on the board is actually, so you had 1, but with the noise it became 0.9. Is that what happened?
Yeah, this is with noise, but
Without noise it would have been x squared minus 1. Is that correct?
yes.
Okay, thank you for clarifying.
Okay, so back to this question though. So because the sample moments are random, each of these terms has a variance to it, right? Each of these residuals. So we choose the weight lambda so that the variances are equal.
So the variance of the first term and the second term.
Yeah.
Mm-hmm.
This is the heuristic thing to do.
Okay. And in general, you would like try to equate all variances if you have like more.
Yeah.
Mm-hmm. And also, like, when you talk about spherical harmonics, so am I right that they are like, if you add next degree, this is like an universal representation plus like some of the previous ones, right? So when you increase degree of truncation, you get a lot of different irreducible representations of SO3.
Yes, yeah, you add in it, the next one.
The next one each step.
Yeah.
Okay. That's interesting.
More questions?
I had a question about, you make the assumption that the variance is very large.
Yeah.
And what actually does this? Why is this variance very large? It's not a mathematical question, it's just...
Yeah, it's because the cryo-EM images are so noisy. And the reason that they're noisy is if you shine too strong of an electron beam at the molecules, you actually destroy the molecules, you burn through them. So you're not taking pictures of the correct thing anymore. So it seems like there's a limit to the quality of images.
Okay, thank you.